Let's see just how sharp your intuition really is. Ready to stretch your brain? Picture this. You're standing in a room packed with 1001 people. Yes, it's snug in there. A true math enthusiast's party, where there's hardly room to shuffle your feet, but endless ways to shuffle ideas. Now, here's the deal. Everyone in the room gets to pick a number between 1 and 1000. You jot your choice down on a card, holding it tight like it's the pin to your bank account. This is a solo mission, so please do not copy. The challenge? One by one, everyone reveals their number to the group. Your goal is simple but intriguing. Figure out how many people need to reveal their numbers before we can be 99% sure that at least 2 people have picked the same number. Sounds straightforward, right? But don't let that fool you. It's a dazzling puzzle of probabilities. Here's a teaser to help you. To be absolutely certain that there's a match, you need all 1001 people to reveal their numbers. Why? Well, think about it. There are only 1000 numbers to choose from. If everyone miraculously picks a unique number, we're in the clear. But the moment that 1001st person steps forward, they're out of luck. There's no new number left. They're forced to pick a number that's already been claimed, and voila, we have a match. That's the power of the pigeonhole principle, a beautifully logical idea where math meets the undeniable truth of limited options. Imagine trying to cram 1001 pigeons into 1000 little holes. At least one hole's going to get cozy with more than one bird. It's the same reason your suitcase always ends up overstuffed when you try to bring 12 pairs of shoes on a weekend trip. Too many items, not enough space. But we're not aiming for perfection. We do not need 100% certainty here. Instead, we're shooting for a solid 99% probability. Close, but not absolute. Now, here's the question. How many brave card flippers do we need to reach that level of confidence? Is it 900? Maybe 800? 700? Or could it be surprisingly fewer than you might think? Take a moment, really think about it. Don't rush to a conclusion, take a moment to really think it through. What's your best guess? How many people need to reveal their numbers for the math to work its magic and lock us into that elusive 99% certainty? The answer might just catch you off guard. In fact, it's one of those cases where your intuition could lead you astray. Think you've got it figured out? Let's see if the numbers agree with you. We're going to unravel this step by step, and I guarantee it'll be much more fun than it sounds. It's not just about numbers, it's about understanding how probability shapes the way we think, make decisions, and sometimes misjudge the odds. Ready to dive in? Let's take this journey into the world of probability together. You might just end up with a whole new perspective on how math really works behind the scenes. How many chances are there that we see the same number after the first person flips their card? Well, at this point, it's a lonely world. Only one card has been revealed, so there's absolutely no one else to compare it to. The probability of seeing a match is, quite simply, 0%. It's like being the only person at a party, no awkward moments of spotting someone wearing the exact same outfit. What a way to stand out and be truly unique. How many chances are there that we see the same number after the second person shows his card? Now it gets more interesting. The second person has 1000 possible numbers to choose from, and one of those numbers matches the first person's card. The probability of a match is 1 over 1000, or 0.1%. So, there's a tiny chance of déjà vu here, a 0.1% likelihood that these two people will share a number. Cute, but still not what the probability we're looking for. The suspense is building though, so let's keep going. The third person steps up, card in hand, and the stakes are higher. The third person has 2 opportunities to match someone. They could match the first person's card or the second person's card. However, we can't simply add probabilities here because we'd end up double counting cases where all three might match. Instead, we calculate the chance of no matches and work backward. So, let's calculate the probability of no matches at all. For no one to match, all three cards need to show unique numbers. The first person can pick any number, so that's a 100% chance. The second person must avoid the first person's number, so they have 999 choices out of 1,000. The third person must avoid the first two numbers, leaving them with 998 choices out of 1,000. The probability of no matches at all is product of those probabilities, which is approximately 0.997. Now, to find the probability of at least one match, we subtract this from 1 and we get 0.3%. So, after the third person reveals his card, there's a 0.3% chance that at least two people share the same number. The odds are still small, but they're steadily growing like the anticipation before a jackpot-winning lottery draw. Now, it is simple to generalize it. To calculate the probability that at least two people share the same number after the nth person reveals his card, we will first find the probability of no matches after n people. For no matches to occur, every person must pick a unique number. The total pool of numbers is 1,000. As each person picks one number, the pool of available unique numbers shrinks by 1. So, the probability is the product 1,000 over 1,000, 999 over 1,000, 998 over 1,000 and so on until we 1,000 plus 1 minus n over 1,000. Note that each number in the product is less than 1, meaning it will shrink each time a person reveals their card. To find the complement event, at least two people choose the same number, we subtract the odds from 1. Alright, it's time to crank up the math machine, or just a Google sheet, and let the numbers do the talking. Using this magical formula, we're going to calculate the odds in juicy steps of 10. Why steps of 10? Because who has the patience for 1 by 1 when we can fast-track the suspense? And, of course, we'll unleash the ultimate plot twist, a graph. Yes, a graph. The universal language of nerds and overachieving statisticians everywhere. Let's see how those probabilities shape up. When n equals 10, the probability sneaks past 4%, just a hint of what's to come. By n equals 20, it leaps to over 17%, the suspense builds. By n equals 30, it soars above 35%, and you can almost feel the inevitability setting in. Then, at n equals 38, the game changes entirely. It's officially more likely than not that at least two people have chosen the same number. That's right, math is no longer playing coy, it's laying its cards on the table. But hold on, don't leave the party yet. Now, let's see how this probability roller coaster picks up speed. At n equals 50, we're already past 71%, meaning the odds are looking pretty good for a match. By n equals 60, we're pushing 85%, and by n equals 70, it's a solid 91%. We're almost there, folks. N equals 80, the probability is over 96%. At this point, it's practically a done deal. But hold on, things are really heating up. By n equals 90, we're over 98%, and when n equals 95, we're cruising above 99%. The match is practically knocking on the door. This math magic is about to reach its grand finale. Yes, the answer is 95, that's it. So low! Did your gut feeling line up with the math here? Or were you completely thrown off? When you first heard about the problem, what did you think the magic number would be? Maybe you thought we'd need a crowd of 500 or even 800 people for that first match to appear. If so, you're not alone. This is what I call the lottery paradox, the sneaky way our brains seriously underestimate the power of probability when it comes to seemingly random events. It's like buying a scratch-off ticket and thinking, surely, I'm due for a win, right? Spoiler alert, math's got other plans. So take a deep breath and reflect. Did your first guess completely miss the mark? Or did the odds fall into place just like you thought? Let me know in the comments below. Either way, you've now got a fresh party trick that's sure to get people scratching their heads.